So this video is on proof by contradiction. So proof by contradiction is a really powerful type of proof. So here's an example question where we need to prove by contradiction that root 2 is an irrational number. So for any questions, the question will directly tell you to use proof by contradiction, and then it will give you a statement that you need to prove by proof by contradiction. So for proof by contradiction, there are 3 steps that you need to do to answer each question. So the first step that you need to do is you need to assume the opposite statement to what's given in the question is true, and you need to write this down. So for this question, we're going to assume that, so the statement is that we need to prove that root 2 is an irrational number, so we're going to assume the opposite, that root 2 is actually a rational number. So you just write down the opposite, or assume the opposite, of what you're trying to prove. And then the second step is to prove the assumption that you made here is false, and you need to contradict it. This is kind of where the proof by contradiction comes from. So this is basically the actual mathsy part of the proof, and for this question we'll go through in a sec how to do it. And then the final step is the step that we've done for proofs before, where you just write a statement at the end. So you say therefore, so these 3 dots mean therefore, remember. The statement is true. So for this question, it will be therefore with these 3 dots, and then we just repeat the statement up here. So therefore, root 2 is an irrational number. So template all questions like this. So what you do, you assume the opposite statement to what you're trying to prove is true, then contradict that and prove that that is false, so therefore the opposite is going to be true, so therefore the original proof is therefore going to be true. So let's go through this example. Let's prove by contradiction that root 2 is an irrational number. So this is specifically mentioned on the spec, along with another example that we'll go through in a sec. And for both of these, I would personally learn them off by heart, or just kind of remember how the technique works, as they're specifically mentioned on the spec, and they're also quite hard in my opinion. I couldn't do this from scratch. I just remember how to do it from looking at the book. So just a reminder, we went through this in the rationalizing denominators video in more depth, but a rational number is a number that can be expressed as the fraction a over b, where a and b are integers or whole numbers. So this is something like 3 over 2, or 1 over 4, or 5, because this can be expressed as 5 over 1. Irrational numbers are the opposite, where we cannot express them as a fraction, where a and b are integers. So this is something like pi or e, or root 2, which is what we need to prove. We need to prove that root 2 is an irrational number. So how do we do this? Okay, well, it's proof by contradiction, so please follow the template from before, because that's kind of the way that you get the marks. That's what they're looking for. So the first step is we need to assume the opposite statement. So the question wants us to prove that root 2 is an irrational number, so therefore we're going to assume that root 2 is a rational number. Okay, so what can we do with this? Okay, well, if root 2 is a rational number, let's use this. Therefore, root 2 is equal to a over b, where a and b are integers. This is just what we did before. And another important thing that we need to clarify, a and b have no common factors. So therefore is in its simplest form, a over b. So what does this mean? Well, basically, we've expressed it as the rational form here, a over b, where a over b are integers. But we need to clarify that a and b have no common factors. Because remember how you can cancel down fractions. If you times both the top and the bottom by times 2, this is the same fraction, but it is no longer in its simplest form, because you can divide both the top and the bottom by times 2 in order to get it in the simpler form. So what we're saying here is a and b have no common factors, so a over b is the simplest fraction. It cannot be cancelled down in any way. Okay, so let's do some work with this. So therefore, if root 2 is equal to a over b, we can square both sides and say that 2 is equal to a squared over b squared. And then let's times both sides by b squared to get rid of the denominator. So 2b squared is equal to a squared. So therefore 2b squared is even, which makes sense because remember we're timesing it by 2, and any number that is multiplied by 2 will automatically become even because it's going to be times by 2, so 2 is going to be a factor. And as 2b squared is equal to a squared, therefore a squared is also even. So therefore a is even because any number that is squared and it's even, therefore its square root is also going to be even. That's the case for all square numbers. So as a is even, therefore we can express a equal to 2n. Now this is something we talked about in the proof videos in chapter 7 in year 1. This might be something you're not familiar with if you haven't watched that video or come across this before. Any number that is even we can express as 2n, and any number that is odd we can express as 2n plus 1, or we can do 2n plus 3 as well. And this is because n is just any number, and no matter any integer, sorry, and any integer that n is, if you times it by 2 it is going to become even. So 1 2 3 if you times by 2 is going to become 2 4 6. It's always going to be even. And this is the same for the odd numbers here. This is just something that you might need to remember, a technique that you can do. A can be expressed as 2n as a is even. So what we're going to do is we're going to rewrite this using this. So therefore 2b squared is equal to, so a is equal to 2n, so it is equal to a squared, so it's equal to 2n squared. We can simplify this to 2b squared is equal to 4n squared, and we can divide both sides by 2 to say that b squared is equal to 2n squared. So 2n squared is even for the same reasons, because we're timesing any integer here by 2, so it's going to be even. And as these two sides are equal, therefore b squared is even. So b squared is even, so therefore as the same thing as before, because a squared is even, a is even, therefore as b squared is even, b is even. So therefore a and b are even. But now we have a problem because we've contradicted this here, that a and b have no common factors. If a and b have no common factors, this cannot be the case if a and b are even, because that means that a and b have a common factor of 2. Because they're both even. They can both be divided by 2. They can both be simplified. So therefore, we have contradicted that a and b have no common factors. And now we've actually done the difficult part of the proof. We have done the kind of the mathsy part of the proof. We have contradicted our original assumption. We said that a and b have no common factors, but we have proved this is impossible because a and b are even, so therefore they will have a common factor of 2. So we've contradicted ourselves and we've done the question, and now we just need to write the statement at the end. Therefore, root 2 is an irrational number. And we've done the question, we've done the proof by contradiction. We said that a and b have no common factors, but they have to have a common factor of 2. So we've contradicted ourselves, so therefore our assumption has to be false, so therefore the original statement has to be true. So just remember for proof by contradiction questions to follow this template of the one that I showed before. So here's the other example that's specifically mentioned on the spec. We need to prove by contradiction that there are an infinite amount of prime numbers. So remember the first step, we need to assume the opposite of what we're trying to prove. We're trying to prove that there are an infinite amount of prime numbers. So therefore, the statement is we're going to assume that there are a finite amount of prime numbers. Okay, so what can we do with this? Well, if there are a finite amount of prime numbers, Therefore, we can create a list of all prime numbers. And this list will be P1, where P1 is the first prime number, P2, where P2 is the second prime number, P3, where this is the third prime number, and this goes all the way up to Pn, where Pn is the nth prime number, and this is the last prime number. And it doesn't actually matter what n is. N could be massive, it doesn't really matter. But the point is that it is a finite amount of prime numbers. There are no more prime numbers after Pn. This is the final prime number. So therefore there are a finite amount of prime numbers. Okay, let's create a number called n. And let's say that n is equal to all of the prime numbers multiplied together. So it's going to be the first prime number times the second prime number times the third prime number, all the way up to the nth prime number. So we have times every single prime number on this list together. So we have prime, because it's a finite amount of prime numbers, we have times all of the prime numbers together. And let's add 1 to this final number. We've times all of the prime numbers together, and then let's add 1 onto this final number. Well, therefore, n, when divided by any prime number, has a remainder of 1. So let's step back for a second and see what we're saying. So let's get rid of the plus 1 for a second. Let's say n was this. If we therefore divided n by any of the prime numbers, it would be divisible by any of the prime numbers, because we have just times all the prime numbers together. So it would be divisible by P1, divisible by P2, divisible by P3. But as we've added 1 on the end, it is now not divisible by any of these prime numbers. It always leaves a remainder of plus 1. So therefore, as n, when divided by any of the prime numbers, has a remainder of 1, therefore n is a prime number. Now this might be a bit of like a jump in logic in terms of what's going on. Well, basically this is the case because n cannot be divided by any of the prime numbers now, as we said, because it has a remainder of 1. Now you might say, okay, but what happens if we divide n by something that's not a prime number? So for example, 15 is not a prime number. Well, 15 is equal to 5 times 3. So if n is divisible by 15, it has to be divisible by 5 and 3 as well. But 5 and 3 are prime numbers, and we have proved that n is not divisible by any prime number because it has a remainder of 1. So therefore, because all numbers, all non-prime numbers, have prime number factors, therefore n cannot be divisible by any normal number either. So therefore n has to be a prime number. But therefore we've made a contradiction. We have contradicted that the list has all prime numbers. Because it doesn't now, because we found a new prime number. We have found that n is a prime number, but this wasn't included in this original list. The final prime number was Pn, but we have proven that n, which is times by Pn, so therefore it's bigger than Pn, is not in this list. So therefore n should also be in this list as well. So we have contradicted that the list has all the prime numbers, so we've done our contradiction. So we've done the question, and we just need to make the statement at the end. So therefore there are an infinite amount of prime numbers. And that's it. We have proved the question. We have proved that the assumption that we made, or part of it, is wrong. We've done it wrong. It's contradicted itself. So therefore the original statement has to be true. So as I said before, these two examples, this and the root 2 is irrational proof by contradiction, are difficult, and they're specifically mentioned on the spec. So I would remember how to approach them, because it's a bit weird. The other example in this video is a bit more self-intuitive, and you could do yourself, but these ones have weird methods I would sort of kind of memorize the technique of. So this is the only question so far that they have asked on the new spec on proof of contradiction. This is something that wasn't covered on the old spec, so there are no old questions on there. Okay, so let's do this question. So we need to prove by contradiction that there are no positive integers p and q, such as this is true. So first of all, we need to write down the assumption of the opposite thing. So we need to assume that there are positive integers p and q such that 4p squared minus q squared is equal to 25. Okay, so what can we do from here? So firstly, hopefully you realize that this is actually a difference of two squares, that we can write this. So 4p squared minus q squared is equal to, and we can write this as a difference of two squares, where if we square root this, this is 2p, and this is 2p, and if we square root this, this is q, and this is q, and this will be a plus, and this will be a minus. So therefore we can write this as 2p plus q, 2p minus q is equal to 25. So firstly, we need to realise that 2p plus q and 2p minus q, if there are positive integers p and q, therefore these are also integers. If p and q are integers, then therefore 2p plus q has to be an integer and 2p minus q has to be an integer. It can't be like a fraction or a decimal or something like that. So therefore these need to be integers. So therefore we need to find two positive integers that multiply together in order to give 25. And there are two scenarios for which this has occurred. One is 5 times 5 and the other one is 25 times 1. So therefore there are three scenarios for which these two integers can multiply together to give 25. The first one is when 2p plus q is equal to 5 and 2p minus q is equal to 5. And then the other one, or the second one, is when 2p plus q is equal to 25 and 2p minus q is equal to 1. And then the final scenario is when 2p plus q is equal to 1 and 2p minus q is equal to 25. These are the only scenarios for which 2p plus q and 2p minus q are integers and multiply together to give 25. So these are the only possible solutions. So let's solve these individually. So these are a pair of simultaneous equations which we can solve. So for this one, I'm just going to rearrange to get 2p minus q minus 5 is equal to 0. And this is equal to 2p minus 5 is equal to q. And then we can sub that into here to get 2p plus q, which is equal to 2p minus 5. So it's going to be 2p plus 2p minus 5 is equal to 5. So this is 4p minus 5 is equal to 5. So this is 4p is equal to 10. So therefore p is going to be equal to 10 over 4, which is equal to 5 over 2. Now just for completeness, if you sub p into here, you get that q is equal to 0. This doesn't matter because we've already proven this solution doesn't work because p is equal to 5 over 2, which is not a positive integer. So for the second pair of simultaneous equations, we do the same thing. We rearrange this to get 2p minus q minus 1 is equal to 0. And then we can rearrange this to make q the subject, 2p minus 1 is equal to q. And then sub that into here to get 2p plus q, which is 2p minus 1, to get 2p plus 2p minus 1 is equal to 25. So this is 4p minus 1 is equal to 25. So 4p is equal to 26. So therefore p is equal to 26 divided by 4, which is 13 over 2. Again, for completeness, q would be equal to 12, but this doesn't matter because p is equal to 13 over 2, which is not a positive integer. So this is not a solution either. And then the third example, we'll do the exact same thing. Rearrange this to 2p minus 25 minus q is equal to 0. So then 2p minus 25 is equal to q. And then sub that into here to get 2p plus q, which is 2p minus 25. Is equal to 1. This is 4p minus 25 is equal to 1. So therefore 4p is equal to 26. So therefore p is equal to 26 divided by 4, which is 13 over 2. And then if you sub in this into here, you get that the value of q is equal to minus 12. But again, this doesn't matter because this is already not a positive integer. So this is not a valid solution. So therefore, we have proved that there are no solutions when P and Q are positive integers. So therefore we have our contradiction. We have contradicted our original statement that there are positive integers P and Q such as that. We have contradicted this, there are positive integers P and Q where 4p squared minus q squared is equal to 25. So we've done all the hard work, and now we just need to write a statement at the end. We've contradicted this, so therefore there are no positive integers P and Q such that 4p squared minus q squared is equal to 25. And that is the final answer. If you write all of that, you will get all 4 marks for this question. So as I said, this is the only exam question they have asked on this so far, and there are none on the old spec, so I haven't included any more examples in this video. But of course, there are loads of examples, proof by contradiction, in the textbook.